Okay, and just so we're legal here, um, on the course web page, if you go to the homework, here's the next homework. We don't have one due on Monday. It's due on Wednesday. Of course, we'll have a quiz on Monday. And then I updated this. If you're not on the Google group, what can I say? Good grief. But one thing to notice here is that this command here will enable compression if you're off campus and speed up the communication a little bit. I also cleaned up, or I went to the bottom here and I changed the discussion on the CDS lock file, because that's going to be an issue for you, and I gave a separate link in case you don't like the way I explain things. And then if for some reason the NCSU stuff was offline and people were saying, oh, I can't get it, and of course all you have to do is go up and type this path in, and then you can see everything that we do in this course. So for example, if I wanted to back up what I've been doing in the class, let's say last time I did this C5 F14, how would I back that up so that if I lose information I can come back and get it? Gee, how about I do the following? This is how easy it is. That's why I get frustrated when you come to me and you say, I lost everything in my project or my homework. Can I get extra time? No, you can't get extra time because I've told you so many times to back it up. So I go like that, save it to the desktop, and it says, okay, there, done. Everything we've done in class now is in this folder. I can go, oh, add to archive. And then the way I do it is I take that archive and I email it to myself so that I have a backup. See how very easy it is to back things up. Okay. Bye. And of course, I'm not backing things up in the class, so maybe at some point I should, because if that directory gets messed up, then I don't have everything we did. So, all right. Let's talk today about the well. And this is the first layer we're going to use or learn about in the course, and we're going to go through step by step what all the different layers are. And so there's really important you understand the difference between a layout view and a cross-sectional view. Does everybody understand that already? No? Yes? Okay. So if I look at the top of, let's say that I have a cake, or let's say a pie, because my last name's Baker. So I take a pie and I look from the top, and I might have some crust, and then around the crust I might have some whipped cream that goes around here, and then I have some filling in the middle, and then maybe in the very middle I have some nuts on the top. Okay, this is the layout view, or the plan view if you prefer, or the top. Okay, when we draw layouts, we're going to look at it from the top view. And so it's very important when you're doing design, in order to go from the layout view where you're drawing all the boxes to the cross-sectional view so you can see what's going on in the chip. So if I were to sketch, if I sketch right across here, I cut the pie in half and I flipped it on its side, what I would see is I would see some crust. Then I would have the filling, and then I would have the whipped cream around the edges. Notice it's just at the edges, right? And then in the very middle, I would have the nuts. Does everybody understand that? So if I move the cross-sectional view from here down a little so it doesn't include the nuts, how does this change? It gets narrower, and there's no longer nuts there. And this is the cross-sectional view. And I go through this really, really simple, because we go through this the whole semester and talk about, here's the cross-sectional view, here's the layout view, and I don't want anybody to be confused on this. Are there any questions? Nope. All right, so our first layer is the end-well layer. Now, for some reason, in this class, well, let me even back up. When you draw the plans of a house, you're looking at that house plan view from the top, correct? Do you draw the ground that the house sits on? Or is it assumed that when you build the house, it's built on ground? You don't draw ground, right? It's there. When you draw the walls, you don't say, hey, here's ground, okay? When we do CMOS, we start with, or when we do chip design, we start with a substrate. And so remember, we had a wafer. I showed you that on the first day of class. So this was a wafer. And then generally this wafer is doped with some sort of doping. We'll say p-type, and that's very common, which means it has what kind of atoms? Well, how many valence electrons does silicon have? So if I have p-type, it means it's missing an electron, so this has how many valence electrons? 3. And what's an example material that I might dope silicon with? Boron. Not phosphorus. Phosphorus is 5 valence electrons. So this is boron. Okay, so I drew this circle here. Which view am I using? Layout or cross-sectional view? Layout, the top. I'm looking at it from the top. And it's p-type. So if I say sketch the cross-sectional view across here, you would come down and you would say, oh, I'm going to come down, and what I would have is p-type. Everybody follow that. Okay, notice I did not draw anything. So when I'm doing cross-sectional views in the class and I give you a layout, there's always the p-type substrate there. You don't say, oh, where's the p-type? I didn't draw that in my cross-sectional view. Okay, so let's take and let's put any questions on that. Okay, let's take and draw a box here right in the middle. And I'm going to call that box N-well. And I'm going to blow this up so the box is N-well, and it's right down here. And I say sketch the cross-sectional view at this point. What do you start out by drawing? Remember, this is expanded, so I'm not going to draw the edges where there's no silicon, but what do I start out drawing in any cross-sectional view? Substrate. So I write this as P substrate. Now I didn't draw that, it's not in here, it's just N-well. Then I come down and I draw my N-well, and it looks like a swimming pool, if you will. Okay, easy, right? If I move the cross-sectional view up or down, how does this change? If I move it to right here, what happens? N-well goes away because I'm not drawing through there. If I move it up here, it goes away. I'm going through this super simple because we're going to use this the rest of the semester. Any questions? Okay, N-well can be used for 3 different things. One is a diode. So I use it as a diode, and I'm going to sketch the diode on there. Which side is the anode and which side is the cathode? Okay, let me ask a simpler question. There's a diode. Which side is the anode and which side is the cathode? Top is the cathode, bottom is the anode. What type of material is the cathode? Everybody that took electronics with me better be screaming this. What type of material, is it P or N, is the cathode? N. And so that means the anode has to be P. So let's go down here and sketch the diode. What's the diode on here? The N-well. The cathode is the N-well and the anode is the P substrate. Does everybody understand that? Okay, so I got a question for you. I don't know how I'm going to do it, but let's say I ground the substrate. So this P substrate's a ground. What's the most negative potential that I can have here on this N-well, and why? Which is about what? I can't go any lower than what here? Minus 0.7, right? Turn the forward diode on. 0.6. So I'm going to talk about resistors in a second. One of the fundamental things you can make with an end well is a resistor. And you probably will find that out if you finish tutorial 1, and we'll draw one here doing a layout in a moment. Okay. When you draw a resistor in a chip that's made with N-well or any of the other types of P-type or N-type materials we'll learn about in a few weeks that are in the P substrate, it's not like a general purpose resistor you can go into the lab and put any potential you want on each side. You have to be careful not to forward bias this. So one of the projects I like to give in this class is that of a substrate pump or a voltage pump that's used in flash memory for generating high and low voltages. This is something you need to be aware of when you do the flash memory, or when you do the design. You can't just put an arbitrarily -2 volts on that N-well resistor because it forward biases the diode. Okay, so our first thing the N-well can be used for is a diode with the P substrate. So one of my favorite quiz questions is, what are the 3 things you can do with an N-well? Make a diode with the P substrate. Now I'm going to take this cross-sectional view, and I'm going to go back, and I'm going to sketch it one more time. And here's our box we drew. Layout view. Cross section. The other thing, and I want to get full credit, so what else do I put here? What? P substrate. And I go and I ask, all right, well, what else can I do? I don't know how I do it, but I can connect from one side of the N-well to the other side of the N-well. When I do that, if this is a wire and this is a wire, I can get current to flow if I apply a potential across the 2 leads of the resistor, and I can use the N-well as a resistor. Does everybody see that? Does anybody see that? Okay, I got a question. If I take a pencil and I scrub on one side of this piece of paper with the pencil, and then I put my volt-ohm meter and I measure the resistance between here and here, will I measure a resistance with that pencil graphite? Of course I will. If I move the 2 leads together, what happens to the resistance? It goes down. Okay? If I move it apart, it goes up. If I make the resistor, the pencil scrapings wider, what happens to the resistance? Goes down. Well, I'm going to talk about that exactly here when I talk about sheet resistance and N-well resistance here in a moment. Any questions? So the 3 things that the N-well can do. 1 was diode, 2 resistor, and the 3rd one I'm only going to mention because we don't know, and that's the body or the 4th terminal of the PMOS. Okay, so let's pause and go just draw a box here in Cadence before we return and talk about sheet resistance and look at the process data sheet and all that stuff. So let's go over here, and what do I want to do first? And then press the up arrow a few times. Boom. And here's what I'm using, C5. I'm going to go File, New, Cell View. And I'm going to call this 10K, or let's just call R underscore 10K. What's that noise? The squeaky noise. You guys nervous back there? All right. And then let's go to layout. And now let's see if it works. We hit R10K. The view is, cell view is the layout. We hit OK. This is a little different than the tutorial. Notice that the It's such a small, I'm not going to show the CIW, the command interpreter window. Notice that the layer selection window, if you went through the tutorial, is on the left here, integrated now in this newer version. Okay, see this first layer? That's P-well. That's in a process which uses 2 wells. We don't have that, so we don't use P-well. It may be drawn, but it's ignored. Okay, so plant that in your brains. It's there, but it's ignored. And P-well is used for the body of NMOS. When it sits in the P substrate, it makes a connection. So I'm going to select this layer, and then I could use the bind keys, but instead I'm going to go up here and go Create Shape, Rectangle, or press R, and it's going to be on the NWell layer. Whoops. Connectivity, NWell, Create Shape, Rectangle. What is that? Create. There we go. It's hard with this screen. All right, so there I drew a NWell. And now if I were to sketch that and say draw the cross-sectional view, you'd say, gee, you're not challenging me, and you draw the cross-sectional view. I want to do 2 things now. One is I want to adjust the position, and I could do that manually. Whoops, I'm still, what mode am I in? Yeah, so you see the little square there? That means I'm in the add NWell, so I'm going to hit escape. Then I'm going to go select this and then press Q, and it's going to tell me the sizes. And I'm going to make some mistakes here. I'm going to set the left at 10, the right at 10, the bottom at, how about, let's do 4.5 and 4.5. And I edit it that way. Now, the reason I show you this is you might be inclined to move things manually. If you get used to using the keyboard entry, it makes life a lot easier because then you can precisely set what the sizes are. What we need to do now is we need to verify that there are no design rule errors, and I'll talk about this more in a moment. Now, if I do this and it doesn't work, the problem was, and I covered this last time, if you go over to the tutorials and tutorial 1, if you go down to the setups, does everybody remember this stuff right here last time we went through? If you don't do that, what I'm about to do won't work, and then you'll be like emailing the Google group, I can't DRC, it doesn't work. Okay, you got to do that step. So I'll go over here to verify DRC, and I'm just going to hit OK. And where's my sound? And if you look, there's markers, and let's see if we can see the command interpreter window here. Total 4 errors found. So I want to see what the errors are, so I'll go up here to, what is it? Verify, markers, find, and I'll just say apply, and it says that the SCMOS edge not on grid. What that means, and when we draw our layouts in this process, okay, so this is a little confusing, and I'll have to go over it many times, but the lambda, or the scale factor, is 300 nanometers. So the grid is on 150 nanometers. So I got to make sure all of my lines or all my shapes are drawn on 150 nanometer grid, okay? So let's go over here, or how do so I go here and I hit Q, and I look and I say, is 4.5 microns, what's a micron? I say that, and assuming everybody knows, what's a micron? 1/millionth of a meter, 10 to the minus 6 meters, okay? Is 4.5 and 4.5 on a 0.15 micron grid? Oh, come on. Let me see. I don't know. Let's find out. Well, I do know, but let's find out anyway. 4.5 divide, whoops. 4.5 divided by 0.15 equals 30. Is that an integer? Yes. So I ask, is 10 on a 0.15 grid? No. Oh, no, it's not. So what could I do in order to make this fall on the grid? change it to what? 9, or let's see, what else would be? 9.9. Let's go 9.9. Well, it's 9.9 on the grid. Okay, so let's find out. So let's go verify, DRC, okay. No errors. Any questions? So I hit save. Okay, so does anybody disagree we can draw boxes in Cadence and that there's an LSW? You know, I get the email and I'm like, you can't draw boxes in Cadence and there's no L. I mean, oh, okay. All right, so now we've done it. We'll come back to this later. So let's see, R10K, there's my layout view. Yes. Well, if you want to, you can zoom in and turn the grid on. So let's see. So let's, how do I turn the, oh, the grid's already on. I can try to estimate what the grid is here, you know, halfway between. But let's say I wanted to measure without looking what the grid is, what the distance is between points. So first let's do zoom. And so let me go here, zoom to area Z. Key binding, so let's just zoom in down here. Can you see those dots? Okay. Let's also do the following. We'll have to do this. Display, and then pin names we'll select later, display level, minor spacing, snap, X snap grid, minor spacing, major spacing, dots, lines. You can set all this up to do certain things, you know, to get what you want. But let's say I want to measure from one point to another. Well, first off, just repeating, why aren't I snap? Can you see the dot there where my cursor is? Okay. Why? How do I make my cursor snap to those dots? What can I do? I gotta know. Options, E, and I can go, oh, minor spacing is, let's do 0.15. Major spacing is 0.3. Okay. Whoops, why didn't it? Did I not hit it right? Display. Major spacing, minor spacing, type, dim major dots, X snap, Y snap. It should be working. Oh, let's I want to cover this stuff later. The snap modes, that's the problem. But let's do one last thing before we quit, because I don't want to spend time on this right now till we have an actual layout. If I go to Tools and then I go Create Ruler K or Clear Ruler, Shift K, I can go down here, hit Hide, and go boom, and I can measure and see what the distance is between things. Okay. When I'm done, I hit Shift K and the ruler goes away. All right. Boring. Close. Okay, so let's go back here. Okay, so one key point to note in the N-well resistor is, as a designer, I don't have control over this thickness. Does everybody see that? I can't control how deep the N-well goes into the wafer. All I have control over is the L and the W of the layout. So let's look. Or actually, let's review something. If I take a piece of material with a thickness T, and I come down here, oops, let's go here, etc. And I look at this, and this is length, and this is W, and the resistance then is equal to the material's resistivity divided by the thickness times L over W. So tell me for a moment, does that make intuitive sense? If I increase the length, does it make sense that the resistance goes up? Okay, did we cover this in 320, the ones that took it with me? All right. So if I look at the N-well, I don't have control over this thickness here. So I don't have control over the thickness. I'm going to give this term here a special term. And I'm going to call this the sheet resistance. and it has units of ohms per square. What are L and W? How are they related when I have a square of material from the layout view? Anybody? How are L and W related when it's a square? They're equal. Okay? So, if I take and look at this layout here, if I have three squares, and I ask what's the resistance between the left side and the right side, you would say 3 times r square, where this is r square here. Does everybody follow that? Okay, so let's go back. And just to be complete, the units of this are ohm centimeters. And the units of this are centimeters, and these are both length, or these are both distance as well. Okay, so let's go back and go to the course web page. Right here. And then I want to click right here, Moses information for this process. This is the process we're going to fab the chips in. So I go over here, I click on that link, and then I come down. I can read this when I have time. I can come down here and I can go to test results for on semiconductor C5 run. So I can pick the corners. Let's just pick this one right here, the recent run. And we'll go through every single one of these in this class, but for now let's not pay attention to anything but this term right here and sheet resistance and this N_W. So this says for this particular process run that the N-well sheet resistance was 808 ohms. Okay, there's several practical important things here that we need to keep in mind. And this is something you can tell when someone's new learning design. When they fabricate these, they can't precisely set the sheet resistance. It varies as they fabricate. So when you're doing your layout and you get a resistor and you want it 10K, you're wasting time if you try to, I got to adjust the width to 9.372 to get exactly 10K, because when they fabricate the resistor's value is going to change. What we do instead is we use ratioed resistors when we do our design. Does everybody follow that? And I'll cover that more later. Key point, you don't get precise resistor values. So don't try to make it precise because it's wasting your time. It can vary plus or minus 20%. Okay, what would be a reasonable value to use for this process for the N-well sheet resistance? $800 ohms. Look at it, it's 808. I'm going to round it to 800. Any questions? Okay, so let's do an example. One that you'll be doing in a homework pretty soon. Any questions about this? These units, ohms per square, they make sense? If you vary the L and the W, you don't vary the thickness. Okay, so here, let's do an example. Using the C5 process, lay out a 10K resistor using N-well. Okay, so I know that R is equal to 10K, and that's equal to my sheet resistance R square times L over W, which is 800 times L over W. Any questions? Where did I get the 800? Well, hopefully you know from that process fabrication. This isn't academic. This is real how you do design. There's no academics here. They measure the sheet resistance. So now the next question is, how do I pick L and W? So what is L over W have to equal anyway for it to be 10K? $12.5? Anybody not see how we got that? Okay, so now, if I look at this, here's my n well. This dimension is what? L, and this one's W. Now the next question is, how do I find out what I can use for L and W? Because there's an infinite number of values that will make this equation correct, right? Okay, so let's pause again. Any questions? Let's go back to the course web page again. And I'm going to look here, and I'm going to see that the Moses Scalable CMOS, and I should say design rules, I'll have to fix that, that's a typo, are found here. Okay, what this file does is for every layer we learn in the class, it tells you what are its limitations. So I'm going to go down and look at the first one. I'm going to skip through all this. You can read through it if you want. I like pictures. I'm not a wordy person. I like textbooks that have lots of pictures. So here's the well. And we're using the sub-M, as you saw on the course web page. Sub-M, submicron rules. Sub-M right here. And I look and I say, okay, 1.1, what's the minimum width that I can have for the n well in sub-M? 12. Does everybody see that? Anybody, what does that mean, lambda? Okay, to keep the design rules scalable between processes, instead of saying, oh, this process, like we do in the actual file where we use actual numbers, we're just going to use integers. And for this process, and this is also stated right here, lambda is 300, what we get is the following. And this is confusing, so make sure you understand it. So for C5, lambda equals 0.3 microns or 300 nanometers. So the design rule said that this size had to be greater than 12 lambda, which is greater than 3.6 microns. Does everybody see that? So now, if I ask what's the minimum W that I can have, the answer is 3.6 microns. So if I want the minimum, that's what I'm going to use to minimize the layout area. Questions? Okay, so then I go, all right, well, if W is 3.6, what is L? L is equal to 3.6 microns times 12.5, which equals, what is it? 45? I need to get new headphones. I'm handicapping myself with these. It makes it hard to hear. 45 microns. Are you sure? Okay, I'm going to change it because I want to see an error. Let's go back now and fix our layout. So this is what I want. And I'm going to go back to my layout here. Get fit. Ooh, I'm going to change that. Options. Oh, that's why I didn't refresh the screen. Let's change the minor spacing to 0.9, and how about 9? Or let's go 0.6 and 6. Hit OK. And then let's hit refresh. All right, that's what I did wrong last time. Okay, so I'm going to go over here now. What mode am I still in here? Ruler. So I'm going to hit escape, get out of that mode. I'm going to come back here, refresh my memory. I want my resistor to have a W of 3.6 and a length of 45. So I query that by pressing Q, and I'm going to do top is 1.8. Bottom is, or top is 1.8, bottom is minus 1.8, and then here I'm going to go 22.5 and 22.5. Hit fit, and there's my 10K resistor. Now just to verify, I'll DRC, but I think it's on grid, so we're okay. And let's see what it said. Total errors found 0. All right. Any questions? Okay, so we don't know how to connect to the resistor. All we know is that we can use this as a resistor. So we know one connection's over here and one connection's over here. Does everybody feel comfortable looking at this and going, oh, that's the layout view, and I know how to turn it on its side and sketch the cross-sectional view? I know how to label the parasitic, meaning unwanted, p-n junction or diode between the n-well and the p substrate. I know how, given a layout, I know how to calculate the resistance of that n-well resistor, if I was given a quiz. Any questions? Okay, so let's go ahead and close that for now. And let's go back over here, and I want to look, and before we leave this design rule stuff, so you can see there'll be other design rules here we'll go through, but there's another one called spacing. And the spacing right here between wells of different potential is 18 lambda. And what would be the physical distance? 18 lambda times 3.6 microns per lambda, or I'm sorry, times 300 nanometers per lambda. So let me say that one more time. So this spacing is 18. So if I ask you in the C5 process, because this is for, we're in the sub M, this is for all the processes, what is the actual distance in microns of this 1.2 here? Yeah, it's 18 times 300 nanometers, which is 5.4 microns. Okay, so you might ask, why do I have that spacing rule? This is another good test question or quick quiz question I like. So let's draw a layout. Let's say I have one like this. This is n-well. And then this is n-well. And I ask, sketch the cross-sectional view right there. You go, gee, you're not challenging me. First thing I draw is P sub. Then I come down here and I go n-well. And then n-well. And I ask, okay, well, I know I have a diode here and here, but what do I have between the two n-wells? I've got a parasitic NPN transistor. You can put the emitter on one side, but NPN. If I move these two close together, I get good efficiency emitting from one to the other. I get transistor action. And I don't want this resistor or n-well to be interacting with this one, so I've got to have a minimum spacing of those two. So one of the common questions you might get asked is, what's the reason for having minimum spacing for n-wells? And the answer is to minimize the parasitic bipolar transistor action. Can you, given this layout, sketch the cross-sectional view, then sketch the parasitic NPN transistor on the cross-sectional view? Yay? No problem, right? Okay. All right. Let's do a couple more things, and then we'll, let me see what everybody knows we have a good quiz question, or a quiz today, right? Okay, what's that? All right, it's good to be deaf sometimes because I didn't hear what you said. Okay. Okay, I have a couple more things, and then we'll take our quiz. One is the following. I want to cover patterning, and then I want to cover using ratioed rules. So with patterning, one of the questions you're going to have when you draw layouts is, if I draw two boxes like this and like this that are touching each other on the n-well layer, because that's the only layer we know about so far, is that the same as drawing a single box of the same effective area over here? The answer is yes. Okay? So now, if I take this box, I want you to tell me, or I want to describe what happens, okay? And so I'm going to go through the process steps. So I start out with, well, just generic process steps. So I started with my P substrate. When I expose silicon to air, what kind of reaction do I get? silicon dioxide. And if you have taken a process class, you'll know that the rough consumption, you know that the silicon dioxide, what's another name for silicon dioxide? Glass, right? So you know that the silicon dioxide here consumes silicon. So if my original surface of the silicon is right here, after I expose the wafer to oxygen O2 for a dry oxide or water for a wet oxide, I'm going to consume silicon to get this layer of silicon dioxide. And this is roughly, the depth is roughly 45%. And so up here you get 55% of the overall thickness, okay? All right, so now I take this mask, or I cover the wafer with a resist. And a resist is a material that's sensitive to light, ultraviolet light. And what I do is I make a mask that I can shine light through. This light goes through this opening, if it's a positive mask, goes through the opening where I've drawn my box. Okay, so this is a little confusing because nowadays, in the olden days, they would take the mask and they would set it directly on top of the wafer and they would shine the light through. Things are so small nowadays that they use projection to reduce, optical projection to reduce, and they other some tricks to be able to draw or have a bigger mask, and then they optically reduce it down by a factor of 5. Okay, so I've got my mask up here. And there's an opening, so this is all opaque. You can't see through it. And where the end well mask, or where the end well I drew was, they have an opening, and then it's optically reduced down. I'm not going to worry about that here. And this is called a reticle. And reticles nowadays are super expensive because of the process, because of the sizes. So my light goes through the end well, or I shine light through here. And of course, it doesn't go through these opaque areas. And it hits and changes the material properties of this resist. I then will take this and I will etch the top of the wafer. I will etch away the resistance. The material properties are changed. So now this is an opening. I'll then further etch so that I get an opening all the way down past the oxide directly into the to the substrate. So what I end up getting is something that looks like this. So this is P sub. And then I'll come in and I'll do an implant of N-type carrier, which we already said was something like boron, and that makes the N well. Is everybody clear on that? Okay, so now a couple of things. Notice when I do this resist, the edges aren't well defined. They kind of out diffuse underneath. That's one of the reasons I have problems getting precise resistor values. Okay, so I ask, okay, well, if I can't get a precise resistor value, how do I do design? I want to give you a simple example. Let's say that I fabricate a 10K resistor and it actually ends up being, in the process run, 9.7K. If I take an op amp and I go through the op amp and I have a 10K resistor here and then I use two 10K resistors, I call this Vin and I call this Vout. I know that Vin over Vout is equal to what? -2, right? If you don't know that, come on. Okay, I think that's even in chapter 1 of the CMOS book. Now let's say that if I change these to 9.7K, what is my Vin? Oops, Vout over Vin, sorry. What does my Vout over Vin change to? Same exact thing, right? So now the question is, well, a good question is, well, what changes in the circuit? The answer is the only thing that changes is the power dissipation because I've got different currents going through here. Okay? But my gain doesn't change because I'm using the same value. So I don't want to lay out a resistor called 10K and then a resistor called 20K when I'm doing design with an IC. What I want to do instead is I want to lay out resistors that are a unit value and use that unit value over and over again. Nowadays, when they're designing in these really small processes, like for the chips that are in your phones, they use the same transistor size. They don't even like to change transistor sizes because the characteristics change. So they'll use the same transistor sizes over and over again, and to get more strength, they just put the transistors in parallel. Okay, so this is very common. You don't lay out, oh, I need a 20K, I need a 10K. No, it's correct to use multiple 10Ks. Oh, I need 100K, use 10 10Ks in parallel, or in series rather. Okay, so before we move on to layout, let me just make a comment. So if I look at the layout here, this was L and this was W. And I ask what the resistance is between here. And again, we don't know how to connect to this yet. Okay, if you want to cheat, you can go look at tutorial 1 and find out how we're going to connect to it. But for now, we don't know. So if I ask what is the resistance between the two sides, it's the sheet resistance. And we look that up from the process data sheet. It's like a data sheet for your microcontroller. You get that information times L over W. What happens if I lay something out like this? And this is W. I'm trying to make it, this is W. And then I might have a distance here of L1 and a distance here of, or let's go from here to here, of L2. Well, it's not going to be the overall length here, L1 plus L2, as the original length, right? Because when you get to the corners here, the current that flows on this corner is going to see less resistance or less of a path than the current that flows over here. So the question is, how do I handle the current that flows in the corner? Okay. And the answer is, I break the resistor up into parts. So for this resistor, I get L1 over W times R square. For this resistor, I get L2 over W times R square. And this is 1 square. Would everybody agree? But again, I have the issue where the current's flowing through the resistor like this. So the way I'm going to approximate that resistance is I'm going to write it as 0.6 R square. Any questions? That's just an approximation for the sheet resistance. So now let me ask you a question. If I do that, does the resistance value, I mean, it's not going to be precise, right? Is that bad? No, because I'm already not being precise by using these resistors. It's going to vary with process. And I can go look on that data sheet and I can see, okay, in this process run it was 808, and this one it was 799, and this one it was 802, whatever it is, okay? That's a pretty mature process, so they're keeping it pretty fixed relative to what they would do in a development process. Okay, so one of the homework problems I like assigned, and I don't think I've assigned it yet, is to lay out a resistor, N-well resistor, in a serpentine pattern. So I want to do that as our last example. But are there any questions? Because generally I want to get going soft, you know, kind of slow, but no one's looking at their phone, right? Okay, you got me. All right, any questions? Okay, let's do that, and then we'll have our grade booster, call it a day. So let's go over here. And I'm going to make a, well, I want you guys to tell me what to do. What I want to do is I want to make a cell that shows a serpentine. You know, a serpentine's what we have. It goes up and down like this. Tell me what to do first. What? File. Notice I'm in this directory. If I don't select that and I select one of the others, then I'm not, I remember I set this up for the C5 process. Okay, I don't remember what I set these up for. We could look real quick, but I'm in this directory. That's important. So go to File, New, Cell View. Let's call this R big, Because when I'm doing a serpentine, generally I want to have just a big resistor. Okay, and you'll see that once we draw the layout for a particular size, the tool will actually tell us what the resistance value is for N-well in this process. Okay, so I'll call R big. There's my layout. I got my N-well. I can slide up and down. I can see all these different layers. We'll know what all of those are. We don't use the P-well in the C5 process. It's a N-well process. We make sure we're on that, and then I'm going to go to Create, Shape. I'm going to hit Polygon. Or actually, you can play around with Polygon. Let's hit Path instead. So I hit Path, and the width is 3.6. So I'm drawing a N-well with a 3.6 width. Is that okay? Remember what our design rule was at the beginning? What was the design rule? Here, I'll refresh your memory. What's the design rule? 12? So that's how many microns? 3.6? Is that okay? Yeah. Okay. You understand the reason I'm going through this is I don't want you just pressing buttons until you get things to work. I want you to understand what you're doing. So I hit hide on this, or I just click this window, and then I'm going to just come down here, go up. I'm going to make some errors here. How do I zoom out while I'm doing this? I thought it was Shift Z. Let's find out. Zoom out. Can I do that while I'm drawing here? Sure. I want to do that because then it makes it, oops, come on. Because it makes it easier on me. So I can go through and boom, boom. I'll just be crazy here. Boom. And then when I'm done, what can I do to stop? Escape. Oops. Hit undo. Oh no, I have to start over. Yeah, you double click. So let's do it again. Create. I don't use polygons that often. I like paths. I like boxes. So let's do it again. Yeah, I think I might. Okay, double click at the end, hit fit. Okay, do you think this is going to pass DRCs? No, why? This little thing's too close, right? Let's find out. Verify, DRC, okay. And man, do I hate not being able to see. What? Well, let's see if the tool has a problem. So it's saying that the N-well's at the same spacing, so that would be 6. That's why it didn't. All right, so I could move this, but it's obviously less than 6, which is how many microns? 1.8. Okay, don't get confused on this because you got to quickly be able to switch between the lambdas and their actual sizes. Okay, but this looks like crap, so I want to make it look nice. What am I going to do? Okay, first I'll show you that if I draw a box around here, I can see where the path is highlighted. Whoops, let me get out of this mode. So if I select this and then I hit Q, what is these points right here showing me? These points right here. The coordinates, what coordinates do they correspond to? Like this one, 31, 65, 25.5. Yeah, where your points are, right? So that would correspond to this point right here. Where would the next one be? Right here, right? Okay, any questions? Does this make sense? Okay, so one last time so this is the point where, and hopefully Monday when all 30 people or whatever in lab and you're doing cadence at the same time, there won't be any issues because I'm nervous. You might have noticed I put a lot of effort into making sure everything is understood with the tutorials and the X term and all that. Any questions about cadence? Then let's stop and have a quiz. Yes? Okay, so this is a question about the lock file. So let's go back over here and look at the homework. And then if you look here, okay, so everybody knows I put a lot of effort into doing this. I basically did it twice. Okay, so if I go down, so I went and over Labor Day weekend, I visited my son, and he has a Mac. So I tried this all out on a Mac. And Dr. Greg, and it works, except you need, instead of having the SFTP that you have here once you log in and the SSH terminal, for the Mac you need to download a secure FTP program like FileZilla, or you can do it on Linux as well, okay? But if you're at home, this is why I sent the email to the Google group. So if you're not a member of the Google group, you need to join. If you're at home, you can get a better performance, a little better speed up is if you use compression. And here's the command for that. Okay, so anyway, I went down, I made sure everything was super clear, like I changed to CSIM cluster because I was using a different server before. I went through and did everything over, redid the video yesterday. You probably got the email if you're in the group. So if you get this lock file, so say you're running Cadence and Cadence crashes, and let's say that it crashes and we're editing, what was the cell we were just editing? This cell right here. If I go look in the directory, and this is something we should look at real quick, in the C5 directory, this is important because you'll waste time if you don't understand this. The R big, in the layout, there's a file called a CDS lock. That means nobody can edit that file but me at this time, so that if you're working with a team, which is what you always do in a company, no one can come in while you're editing the cell and edit it at the same time, because that's a waste of time, right? So it locks a cell and tells whoever wants to use it that it's locked. The problem is, if Cadence crashes and you try to, there's a lock file associated with it. So you have to go in and you have to delete that lock file, okay? That's cute. And there's other lock files, and so I put the information right here so that you could delete it. And then also I Googled and found this link here, which is a better or more detailed description. But for what you're doing, you just have to delete the lock file. So the issue is, if you own that account, so no one else is going to be editing your cells unless you set your permissions to public, right? And so there's not going to be any problem if you delete it. The problem is you're going to start Cadence and start running, and then you're going to try to edit that file, and it's going to say, hey, you can't edit that, it's locked. So you're going to have to go in and delete that file and then restart Cadence. Right? I don't know if you need to restart it, but you'll need to use that. Okay, any other questions? And then also, one of the things you're going to find through the this is a big one, because that NCSU was down. Make sure you can go to this directory and copy what we do in class. It's not going to be showing, just type this in, home EE421, ECG 6214, may not be, it may show as well. Anything we've done in class you can copy, just like I did at the very beginning of the lecture, and put it in your directory and do exactly what we did. I'm not hiding anything. Okay? Finally, if you have abandoned processes, like you're on a crappy internet connection at home, you can kill those processes with this command. If you want to see who's gobbling up all the internet or all the server time because they're doing massive simulations or whatever, you can go use ch2 and you can see, what's going on here. I can go through and see who's using what and what percentage of the CPU. Right now, basically nothing's going on here. I can quit. So anyway, I'm trying to make sure all these commands are useful, so if you're not a Unix person, you can get used to it. Any last questions? All right, let's do the